Hi everyone, welcome back to the channel. So 2 days ago, IBM just announced that they have a new 433 qubit processor that's they're calling the Osprey. Yeah.
Sure.
This is following from their kind of roadmap, that they released already a few years ago. You might remember, if you are an avid watcher of this channel, that we discussed the Eagle processor, which came out around about a year ago. That was a 127 qubit system. But this one, which is the Osprey, which is 433 qubits, which is about 3 times bigger. So this is, on the surface, looks like a big advance. So the details of this processor was released in the IBM Quantum Summit. That just happened a couple of days ago. Now, this sounds like some big quantum conference where all the big quantum people in the world come together. In fact, actually, it's more like a sort of IBM showcasing their achievements type of thing. In fact, the quantum people, I'm not really sure they pay that much attention, to be honest. But it's still interesting to see what IBM is up to, because, of course, they have one of the leading quantum computing systems. So we're going to cover today what this new processor entails and anything else that they talked about in this summit. Okay, so as I was saying, the chip kind of looks like this. It's got the qubit layers on the top there, so presumably there's 433 qubits in that top layer, and then they have the readout layers below, wiring layers below, and so forth. So physically, it kind of looks something like this. So, well,
that's small.
Well, it's
Maybe
it's a chip.
Nano scale.
Nano, yeah, I don't know. Probably that sounds a bit small to me. Maybe micro or something. Yeah.
Okay, you call it a processor.
Yeah. So it's actually kind of physically getting bigger. I mean, it's bigger than the last one. Well, I guess so. It looks like the density of the qubits is not changing very much, because it's roughly 3 times the size of the last. So what is the actual difference in the processors compared to the last generation? If you actually look at the release, there's not much information at all, to be honest. This is just about all the information that they tell us. So they tell us that the number of qubits has gone from 127 to 433. Okay, fair enough. The quantum volume has gone up from 128 to 512. I'll just explain in a minute what that actually means. And then, yeah, exactly, yes. And then the CLOPS, CLOPS, has gone up from 1,400 to 15,000. Actually, this is not even on the new chip. This is on one of their old chips, but they kind of just improved one of their old chips. That's just about all the information that they give. This is a lot different to what they had. So if you check out our previous video from last year, when the Eagle processor, that's the 127 qubit chip, when that was released, they had a lot of data, actually. So they had all this, T1 times, T2 times, and we could sort of actually see the performance of the processors. But I think there's none of that this year. So there's basically no information except for just a couple of numbers that they've given out. So there's not much really actually that we can really talk about. So let's at least talk about the things that they did tell us. So yeah, okay, number of qubits, that's fairly intuitive. Obviously the more qubits, the better. IBM, they keep on introducing new performance metrics. And so they push this quantum volume thing, which actually I think people are now starting to use a little bit. And apparently this is a measure of kind of the quality of the qubits. And then now they've introduced this new thing called CLOPS, and then when you hear them talk about this, they just say it as if like it's something that everybody knows. But in fact, this is only something that they introduced as a metric just last year on the archive, and I'm not even sure if it's even published, right? So it's some archive from last year, 2021. So obviously, I'm not surprised that you guys have never heard of it. because they just introduced it last year, right? All right, so what the hell is quantum volume? Or what size of a quantum circuit that you can actually perform kind of reliably, okay? And so what they do is, it's basically a benchmarking tool. They have this benchmark quantum circuit, and what it looks like is something like this. The pi's are like some kind of permutation of the qubits. Okay. All right. And then the SU4 things there, don't worry about the SU4. It's basically just some kind of random 2-qubit gate. Yeah. So they're performing some kind of random quantum circuit, permutations, and then random 2-qubit gates. Okay. Like this. And then they do this for some number of repetitions. Okay. And then at the end of all this, of course, you get ideally some wave function. And then if you measure that wave function, then you'll get some probability distribution, right? Yeah. And then so the probability distribution, some of them will have large amplitudes, some of them will have small amplitudes. Okay. So you order them all. Okay. So you go, okay, this is the most likely one. This is the second most likely one, like this, right? And then you look at the top half of this and you say, okay, these are the ones which are the most likely ones, most likely outcome.
Which can be used, maybe.
Well, this is just a benchmarking tool. Okay, so these are the outcomes which are like supposed to come out, right? Now you do it on your quantum computer, and then if you actually get the states which you were supposed to get, with probability of more than 2/3 of the time, then you say success, good, this works.
This processor
unit
is
yes, this processor is good because I've got the outcomes that I was supposed to get. Okay.
More than 2/3.
Yeah, more than 2/3 of the time. Right?
And that's the quantum volume.
I'm nearly there. But we call that's a good processor, right? If we don't get it, if we don't get those outcomes 2/3 of the time, then that's a bad processor, right? Okay. And then what is quantum volume? So what you do is you say, okay, I'm going to make first I'm going to try a 2-qubit circuit with like 2 iterations of these permutations and the 2-qubit gates. Yeah. And then I see whether, it's a success or it's a fail, right? Presumably it's a success because that's a pretty small circuit. Then you do it for a 3-qubit circuit, and then you have 3 iterations of this. And then if it's a success, then it's good, right? And then at some point, the circuit will get too big for it to actually work properly, right? So basically, the circuit is too complicated for the quantum computer to handle. And then, so that's the first time that it fails. And so the quantum volume is basically the size of the circuit. So in this case, the quantum volume would be 4 squared.
I don't see the volume in it anyways.
Well, okay, I don't know. Quantum area, I don't know.
I think a useful part of the qubit circuit that is useful without any defects or maybe errors.
I think the idea is it's like the largest circuit that you can run reliably. Yeah. But to be honest, actually, it's not that reliable because it's not like you're getting 90% to 99% fidelity of the state. At the end, actually, you just are getting the correct kind of states at the end more than 2/3 of the time. So, and it doesn't even say, which states that you're supposed to get as the most likely or anything like that. It's just like, Anyway, so that's quantum volume. So in this case, the quantum volume is 512. Okay, so what the hell is CLOPS? Okay, so CLOPS, again, this was only introduced just last year. Okay, but it stands for circuit layer operations per second. And roughly speaking, it's like how many quantum volume circuits, and what I mean by that is like that's the largest circuit that the processor can run reliably. A QPU, as in a quantum processor, can execute per unit time. And, they just throw this around as if like everybody's supposed to know this, but actually you really need to read the paper to understand what it is. And so what it actually is something like this. You again start with one of those circuits that we were just talking about, these random circuits, that's some sequence of permutations and random 2-unit gates, right? And basically you run a lot of variations of this circuit. Okay? You can have variations of this circuit because the permutations can be different, okay? So different permutations, but also the rotations of the 2-unit gates might also be different. Yeah. So you can have lots of different variations of these circuits, right? And then the idea is that you run a whole bunch of different variations of this circuit. And you're not supposed to run them sort of all at the same time, because I think what they have in mind is things like these, variational quantum circuits, things like this, where you run a quantum circuit and then maybe you supposed to adjust a parameter, and then you feed that back, and then you run a slightly different circuit based on the measurement that you just did. So it's a kind of thinking of that particular setting where the output of one circuit is supposed to be the input or it changes the nature of the circuit for the next time. So in this grid here, when you are doing, say, the C pi 1, that means one type of permutation with different parameters. You're supposed to do that kind of sequentially, okay? And then so the number of different variations, it's apparently they just fix this, okay? So they have 100 different permutation patterns, and then also 10 different parameters. So actually sort of 1,000 different circuits. Each quantum circuit you got to run like 100 times, and you always need to do that for any quantum circuit, because whenever you measure the state, you get a random outcome. So you need to sort of repeat that. So S is the number of samples that you need to run it for. So that's 100 times. They also fix that. And then D is kind of the circuit depth. So it's log 2 of the quantum volume. Okay. And so the CLOPS, what it is M times K, which is the total number of different circuits that you can have, times S, which is now, 100,000, right? Yeah. Which is the number of times you run the circuit all together. So, all the different quantum circuit types, and then the 100 times repetition for each circuit, and then multiplied by the circuit depth, divided by the total time that this whole computation has taken. And that's what CLOPS is. Basically, what it is how well can you run a lot of different circuits a lot of different times. And I think that also, depends a bit upon your sort of classical computing input too, so that, all that needs to be all optimized. So that's pretty much, so going back to this thing, again, they are saying now that they are reaching 15,000 CLOPS, but actually, again, this is on their old processor, not the new processor. In fact, in terms of the specs of the new processor, it looks very much apparently like the old Eagle processor that we did last year. So I was just reading on a particular blog that the T1 coherence times are in the 70 to 100 microsecond range. This is basically the same as the Eagle processor. This is a slide that I took from last year's. But they want to improve this maybe by several factors and have longer coherence times. But in terms of the processor, that's pretty much all the information that we have. The other things that was covered in this Quantum Summit was basically their new sort of overall architecture for the quantum computing system. So I think they call this IBM Quantum System Two. So it's some kind of modular type of system where they kind of interlink different quantum computers together and then sort of expand in that way. And they also released some new features in Qiskit. That's their, quantum computing coding software. And one interesting thing that they added is this so-called error mitigation. Yeah, which I actually was quite interested just myself for my own kind of reasons. And basically what this is a sort of a cheaper way of doing quantum error correction, if you like. So as we all know, quantum error correction is basically the standard way that we overcome decoherence in quantum computers. However, it's also really quite difficult to implement because, well, often they need, rather complicated operations to actually realize, or, complicated states. But in quantum error mitigation, basically the rough idea is that you just use some classical processing to try and overcome some of the errors that are happening, right? And then so if you repeat your circuit many times, or if you've got a lot of quantum circuits running in parallel, you can just use some classical post-processing in order to try to figure out a better idea of basically what the real circuit was supposed to be. So a simple example of how they do this is, for example, in error extrapolation, they do is they actually deliberately increase or decrease the errors, right? So they say, okay, I'm going to run the circuit with this much error. This time I'm going to run it with more and more and more. And then you plot a graph and then you sort of extrapolate backwards towards like what the error is at zero, right? Yeah, which is the thing that we're trying to do. That's not the only way to do it. People have been...
So what does mean classically there? Like,
well, it's all done in... You get a bunch of data that's originally come from a quantum computer, and then you just stick it into some classical computer, and then you do some kind of processing to try and extract the results which are superior to the actual raw data.
but is that be fast? I mean, like time-wise, computation time-wise, if you're performing on classical?
Well, depends on what you're doing. I mean, I think there's many different approaches, but this is just sort of classical data processing. So I think there's no reason why you can't do this efficiently. Other methods which indeed may be actually quite time-consuming are sort of machine learning approaches too. So, sort of the trend to just make machine learning to do everything. The machine learning algorithm can somehow learn basically the type of errors that the quantum computer actually has, and then it sort of reverses them in some way. Okay. They also have added a new module to perform dynamic circuits. So maybe the classic example here would be like something like a teleportation, right? So this is feed forward. So you do some operation that is a quantum operation, but it's based upon the outcome of some particular measurement. So teleportation, as we all know and love, you perform a measurement. Depending on that, you perform some classical correction to finally perform the teleportation. So they added some things like this to Qiskit. Yeah, that's about it. That's, I think, all that was really released, or that's all that we really know at this point. So I'll hand it over to you. What do you think? Are you impressed?
What type of thing will this one be able to do?
Real world application.
Yes, I think in the other one,
yeah.
I think were they not the people that tried to solve, is it water problem?
Oh, you mean like a quantum chemistry of water?
Yeah.
Well, presumably, yeah. At least more powerful in terms of, quantum volume. so perhaps you could do slightly more complicated molecules. But I mean, actually the coherence times are the same.
Yeah,
and
that CLOPS. Yeah,
so you like CLOPS as well.
It's new words I'm learning. I'm not. But
okay, I suppose quantum volume is supposed to tell you that you can do, larger circuits, right? In principle, yeah, if you believe that. I don't know. I think my general point of view in this whole thing is that these days it's actually not so hard actually to add a whole bunch of qubits, right? Because in a way, all you got to do is print more qubits on the chip, right? And actually, making a whole bunch of qubits is now, in a way, no longer the challenge. D-Wave, whatever you think of them, yeah, they actually have systems that are much larger than this already for many years. But, people attack them for saying that, it's not really quantum, it's not really doing anything. So, it's really a question of what it can actually do now, and can you actually correct the errors. And, I mean, I think actually, if you really look in terms of fidelities of circuits, even in the famous experiments like the quantum supremacy experiments, fidelities are so low actually, right? Like, they're down to like 0.01 or something fidelity, right? Fidelity. That's not errors, that's fidelity, right? That means 99% error, really.
Error, yeah.
I mean, these are some very low fidelities that we're getting really out of these circuits. So can they really do something that is going to be useful? I don't know. I'm not totally convinced.
How much error can they really correct?
The mitigation?
Yeah, the mitigation.
Yeah, that's a good question. I don't know. This is still relatively new. I mean, I think if you go back to this this roadmap that these guys are doing, I think they're still not completely abandoning quantum error correction. So if you look at their thing beyond 2026, they're still talking about quantum error correction. So presumably they're still going to do that. But sort of it's a kind of a thing in the meantime type of solution, I think. It's a sort of a NISC type thing, right? It's like, what can you do with the things that you got? At least for the systems that we're dealing with now, this seems to be a reasonable approach. Yeah. So you can see that I think they're thinking about like interconnecting different chips now.
About efficiency, I don't know how efficient it will be, but maybe increasing the processing, the overall time, overhead cost, maybe it will.
But it is like multiples of, I think, older ones. Like if they have prepared counter and then they are just repeating.
When you say increasing the efficiency, so would that mean that the fidelity will go up or go down, or the speed will go up?
That will depend on the basic building block. Yeah, but it is for connections.
I sort of get the feeling that they're going towards this classical quantum hybrid thing a lot, because if you actually look at some of their pages, now there's like a big page saying something like quantum-centric computing. Sounds fancy and whatever, but I think what's nuanced there, and quantum-centric computing is not really an academic word, right? This is another IBM kind of marketing kind of thing. I think what's nuanced there is actually that it's a bit of quantum, but it's a bit of classical, and then you sort of use a bit of the quantum to
process or something.
Okay, in the good case, speed up your calculation, in the subroutines. In the bad case, just make yourself feel better that you're using quantum. And then and then merge these two things. I feel like there's a little bit of a deviation from, the ideal kind of sense of the quantum computer. Yes, I'm going to run Shor's algorithm and, it's fully quantum calculation and boom, I'm factoring numbers exponentially faster, right? Seems like, interconnecting these processes is sort of going to be like, outsourcing your whatever processing to processors, and then you run them on there and then you collect them back and you do some algorithm. I'm not sure if I'm explaining myself very well. Yeah.
I understand what yes.
Okay. Anything else you want to add? Why are you such a fan of this word?
Because I I was thinking in terms of some density of the circuit.
Oh, you're graduating soon. This is why, right?
I'm just more
you want to work at IBM, yeah. All right. Okay, we'll leave it there. So thanks for watching. See you next time.